Okay, we're going to continue with number 18, and it's chloroacetic acid has a pKa of 2.87. Let me go through pKa. We didn't have time on Thursday to finish that, but here's the PowerPoint, and it's on the homework already. And you got the pKa. I hope you were supposed to read the book, the Learn Smart. But anyway, I hope. pKa is the minus the log of the Ka, basically like the pH. And a low pKa, it's a high Ka. pKb would be the same thing. And pKa, how I said, the lower the pKa is like the higher the Ka. And Ka plus, multiplied by Kb gives me Kw. But we'll do that on Monday. And you don't have to worry about this right now. So, um, pKa of 2.87. Let's keep on going with this problem. What are the concentrations of hydronium HO plus 3 pH and concentration of Cl CH2 COO negative? In 1.95 molar of the acid. So you got here Cl CH2 COOH plus water. I'm writing the ionization. Again, I made the same mistake. So plus water, weak acid, equilibrium, H3O now, plus Cl chloroacetate, CH2 COO negative. And it's 1.95 here. So what is the first thing? The first thing we're going to do is first find out the Ka. Okay? The other one is the ICE, because here we got zero concentration here and zero. Here's the ICE. But let's get rid of the Ka. Have the Ka already. So you got that the pKa equals 287 2.87. So Ka would be equal to the 10 to the minus pKa. We've done it with we did it with the POH and pH. 2.87. It comes from this. Ka equals 10 is the same to the minus pKa, and this is because pKa is equal to the minus the log of Ka. So when we want to go the other way around, then we have to do to the 10th. So Ka would be equal to 10 to the negative 287, and that gives me a Ka of 1.3 times 10 to the negative 3. So this is a very, very, it's a not very, but it's a greater Ka. So I wouldn't drop the term. Yeah, but you can. Okay. So here, the change would be minus x, x, and x. So here would be 1.95 minus x. I forgot to plus x here. X and x. So let's write the equilibrium expression, and it would be Ka equals, let's look at the ionization. H3, okay. Hydronium multiplied by the concentration COO negative divided by the concentration of the acid. Okay. This is going to be 1.3 by 10 to the negative 3 equals, then here is x to the square because it's x to x, right? And here on the bottom, 195 minus x, the acid. 95 minus x. So can we round it? Can we drop this x? Well, I was thinking, okay, this is a minus 3, and it's very difficult, but look at this concentration. I would risk it because this concentration is high, 1.95. So let's do something. Let's go ahead and try, and I would try to drop this x, and then we'll double check. Do you see, when you see a bigger concentration like this, more than 1 here, almost 2.0 molar, and even if this is not to the minus 5, you still can try. If this is small, and this Ka is great, it's large, it's high, like 1.3 10 to the negative 3 compared to 1.8 times 10 to the negative 5. Then you cannot do it, but 195 is high. So we're going to drop it, and it's 1.3 by 10 to the negative 3 equals x to the square divided by 1.95. So we got 1.3 times 10 to the negative 3 multiplied by 1.95 equals x to the square. So this is 2.535 by 10 to the negative 3 equals x. I got the square root on both sides. So x would be 0.05035. Then we'll round it to the number of sig figs. But let's try the 5%. And the way of doing it again is 0 point to see if the drop was reasonable and was acceptable. 0.35 divided by 1.95, okay, this divided by this by 100 equals so this is going to be 2.58% or 2.6%. Of course, this is less than 5, so dropping the term x, the x was correct. So x would be the concentration of the H3O plus equals to the concentration of the conjugate base here, right? They're asking for the two of them. CH3 COO negative and equals to the X, which is 0.0504 M. Okay. And the next one would be the concentration of the acid in equilibrium. I always forget to put the AQ, don't forget. But it's the same here. CH3 COO is basically the same here because in acid base, because this is the initial given and then you have it in equilibrium after ionization or the ionization of the acid. So this would be initial was 1.95 minus 0.0504 dx. The concentration of the acid in equilibrium would be equals to I don't see it. So equal to 1.95 minus 0.0504 equals 1.8. It's going to be 1.8996. So equals 1.90 molar. Yes, I saw it, but okay. And then finally, the pH would be minus the log of H3O plus, the concentration of hydronium, and this would be, which is 0.04, is going to be pH equals minus the log of 0.0504, and pH would be equal to, if you do this, it's going to be 1.29. Or 1.30. Remember, you have to round it to 2 decimals. Okay. So we got the next one, 19. Let me go faster because... Okay, hypochlorous acid, pKa, again. It's basically the same. pKa is giving up 7.54. Okay, and they're asking only for ClO in 0.115 molar of the acid. Okay, so we write our equation and we find out pKa. There, with the pKa of 7.54, we can find out, let's do this first, we can find out the Ka, and it's equal to 10 to the 10 to the minus 7.54, which gives you a Ka of 1.3 by 2.9 by 10 to the negative 8. 2.9 times 10 to the negative 8. So it's going to be here. Okay, let's write the equation. Now when we decide when we get to the dropping the x, forget about it. This is negative 8. And this is your problem because there's a lot of dropping x. A lot. There's only a few that we have to do the equation. H3O plus the quadratic plus Cl negative. So we got here, okay, that Ka equals but before, let's do our IC again. You probably know it by now, but we have to do it. And it's our ice. I know. 0.115. And of course, see, we are always ignoring the water, don't forget. So here the change would be minus x, x, and x. Well, meaning that we always ignoring the water or the H2O without being dissociate. So the ionization of water is going to be 0.115 minus x, x, and x. So it's going to be Ka. I always do directly the change without the equilibrium without doing the change most of the time. H3O, ClO negative, and this is, so Ka would be, we found the Ka was 2.9 by 10 to the negative 8 equals x to the square divided by 0.15 minus x. And compared to the 0.15, we drop this one and it's going to be 2.9 times 10 to the negative 8 equals x squared divided by 0.15. So x would be, again, the same thing, the square root of 2.9 by, this is the same that we've been doing, 0.115. So x would be, the square root of this is, I'm going to do it directly. If you have any question, text me, please. And it's going to be 5.77 times 10 to the negative 5. So the concentration of H3, and of course, if you check the drop in the term, you put 5.77 times 10 to the negative 5 divided by 0.15 by 100. Forget it. This already, you know, is less than a 5%. I'm double checking, but you know. So the concentration, you can finish this, the concentration of this would be, this is only what they're asking for. So it's the X, okay? So the X, this is the concentration of ClO negative. Okay, let's go and do the next one. Okay. The weak acid HQ, number 20 now. HQ has a pKa, again with a pKa, 4.89. Calculate the concentration of H3O plus of, this is what the problem is asking for, and it's telling you that the concentration of HQ would be 0.025. This is any acid. So 0.025. So we got here that HQ plus water, ionization, H3O plus Q minus. Let's find the Ka, and it's gonna be Ka equals 10 to the minus 4.89. So Ka equals 1.3 times 10 to the negative 5. Okay, so we got, here we got the ice table, And we got 0.025 x x. Here the change would be minus x. Ah, again. Okay, I made a mistake. It's 0 and 0. So it's going to be minus x. Here is 0 and 0. And here is going to be plus x. Plus x. And then we got 0.025. You probably already know this by memory. Minus x and x here. So this is going to be Ka. I'm going to do it directly. Was 1.3 by 10 to the negative 5. If you remember, we got it here. Yeah? Equals x to the square divided by 0.025. We've done it so many times that by now you probably know it by memory. So this is going to be, again, we can drop negative 5, but we need to verify because look at this concentration, it's very small. So it's always good that we check it out. So this is going to be 1.3 times 10 to the negative 5 multiplied by 0.025 equals x to the square. And this gives me 3.25 by 10 to the negative 7. And to get the x is the square root of this. And the x is going to be equal to 5.7 times 10 to the negative 4. Now let's verify, like I said, again, that when you drop this, you're on. It was correct. 5.7 5.7 times 10 to the negative 4 divided by 0.025. This is the term, okay? Equals by 100 equals 2.3%, less than a 5%. We don't need to do the quadratic equation. You see here. So the concentration of H3 plus is going to be 5.7 times 10 to the negative 4 molar. And I don't know if this is all what they're asking for. Yeah. Okay, let's go with number 21. Aspirin is the most widely used term. Find the pH. Just asking for the pH. Okay, of 0.049 aqueous aspirin. Okay, of the acid acetylsalicylic acid H9 C9H7O4, and says find the pH, and the Ka given is 3.6 by 10 to the negative 4. Why is it that it gives you a 37? And this is for review because it's going for the test too. And it said K changes with temperature. Okay, so we got here HC9 H7O4. That's the acidic acid hydrogen, the one here, plus H2O equals H3 plus C4 C9. Oh my goodness. It's the time of the day, the morning. Okay, here is C9 H7O4 negative O4 conjugate base of the aspirin. Okay, this is simple. We have to find here the pH. So the first step would be IC, because Ka is given, concentration of the acid is given. So we do ICE, we find the hydronium concentration, and then we find the pH. So this would be 0.049. But here we have to do the quadratic equation. We're going to have to do it 0.49, 0, 0, 0. The change would be minus x plus x plus x. This would be 0.049 x and x. And so the Ka would be 3.6 by 10 to the negative 4 equals x to the square, and I forgot to put minus x here, equals x to the square divided by 0.049 minus x. So this would be, right, can we drop the x? I don't think so, because this is relative big. Is greater than minus 5, the exponent. And on the other hand, this is very small. So, no, we're going to have to do, unfortunately, the quadratic equation. Solve it by then. So, let's go ahead and start, which is not too difficult. It's not a big deal here. So, it's 3.6 times 10 to the negative 4. And we multiply this by both sides, 0.049, so this goes on top, equals x to the square. We have distributor property, okay? So it's going to be 3.6 by 10 to the negative 4 by 0.049 is going to be 1.764 times 10 to the negative 5 minus 3.6 times 10 to the negative 4x equals x squared. So this is going to be, we take everything to the right side, so that way x to the square stays positive. So we add 3.6 both sides, 10 to the negative 4x, and we subtract 1. That's not that I can. So here would be minus 1.76 times 10 to the negative 5. So now it's the same. X to the square plus 3.6 times x minus 1.76 times 10 to the negative 5 is equal to, write it like that. So this is going to be x equals minus b minus 3.6 times 10 to the negative 4 plus minus square root of b to the square 3.6 times 10 to the negative 4 square minus 4ac, which is going to be minus 4 multiplied by a, which is 1, okay, here, multiplied by c, which is minus 1.76, this one, by 10 to the negative 5. And divided by 2a, which is 2. So here, x would be equal to minus 3.6 times 10 to the negative 4 plus minus this, it's 1.296 times 10 to the negative 7, and here minus and minus gives you plus 7.04 times 10 to the negative 5. And this is basically this, almost, because this is too small. But anyway, let's do it. Meaning that when you add this 2, it's almost this quantity, because this is to the minus 7 and this is to the minus 5. But it changes a little bit, so let's x minus 3.6 times 10 to the negative 4 plus minus the square root of 7.05 times 10 to the negative 5. All this divided by 2. And this is going to be x is going to be minus 3.6 times 10 to the negative 4 plus minus 8.3 times 10 to the negative 3 divided by 2. Now this analysis that I'm going to do now is very important. Why? Because it cannot be negative, the x. So if you take negative 3.6, negative 8.3, that won't be the x. The only x would be possible that you had to take. Oh, sorry. That you had to take is 3.97 is this, minus 3.6. If you subtract both of them, it's going to give you a negative number, and you can't have it. So, but if you add them, times 10 to the negative 3 divided by 2, that gives you an x of, x would be equal to 3.97 times 10 to the negative 3, and this, the concentration of hydronium, would be 3.97 times 10 to the negative 3, which be the same as x. Just remember, we've been doing it. Okay. And this, the pH is the concentration. The pH would be equal to the minus log of the concentration of hydrogen, which is 3.97 times 10 to the negative 3. So pH would be 2 decimals, 2.40. Okay.